Hey. I got it. Okay. All right. So let's see. We're almost done. If you didn't notice, I noticed that we're almost done. The only real assignment that you have left is the second part of MP7. And it's not due for a while. There's one more quiz. You'll have a quiz in lab this week. I think it's heaps and priority queues is the focus of it. Maybe a little bit of graph stuff, but not much. And let's see. Oh, and you're in the middle of exam 7. So everything is sort of in your lap at this point. The final exam will be early in the final window. It's available for you to schedule. It has been for a while. I will continue to talk in more detail about this, but in case you didn't hear it last time, our intention for the final is to take one multiple choice problem per quiz, sort of randomly selected probably. In addition, we'll be doing the quiz that we would have given had we actually had another week of class. So 4 or 5 problems over graphs and graph algorithms. And then probably a couple other interesting multiple choice problems that kind of synthesize your understanding of various data structures. And then 3 or 4 short coding problems. I don't anticipate that the coding problems will be taken directly from past exams, but I don't know for sure. We haven't actually had that conversation. Yeah, Neil? Oh, the quiz you're going to take on prayer learning. Oh, I completely forgot about that. Thank you for reminding me that we owe you some problems also to get credit for the quiz that we forgot as well. You'll all get them. You can do them on your own time, but I keep forgetting to copy them over. Yeah? Oh, you'll decide for yourselves. So you'll have access to the whole exam. You can read through all the problems and let them gel a little bit and strategize yourself. My intention is to simulate exam taking if you were taking it on paper as much as possible, where you have the freedom to navigate around. Okay. All right. Anything else? Yeah. No, I have no information. All right, so let's start working because we have a lot to do. In my mind, we've finished talking about vocabulary and sort of fundamental theoretical notions, ideas that you have to keep track of. We've done kind of graph implementation up to here. Today we're going to finish up graph implementation and we're going to introduce traversal. So we'll still have a little bit of work on traversal to be done after today. And it looks like here's Wednesday, Friday, Monday, Wednesday, and we're at the end of the semester. So we're almost done here. Okay, so before we talk about today's stuff, I want to review just something important from last time. You can see that there's kind of a graph in the background here. And so I want you to suppose that we know the number of vertices. So suppose we know that the number of vertices is, 100. Now I'm going to tell you, whoa, that was cool. I'm going to tell you that this graph is simple and connected, okay? I want you to tell me the most you can tell me about the number of edges in the graph. So here's what you know. The number of vertices is 100, and the graph is simple and connected, and what I want to know is both a lower bound and an upper bound on the number of edges in the graph in this picture. Okay, let's start with lower bound. What goes in the lower bound section? Whisper it to the person sitting next to you. Okay, don't whisper, yell it out then. Okay, 99, good. Good, because this is the result that every minimally connected graph has at least n minus 1 edges. Okay, and what goes in the upper bound here? Oh, you want to say it like that? Okay, I have 100 vertices, choose 2. What's that equal to? Yeah? Very good, 4950. Okay, it is 100 times 99 over 2. Okay, ooh, cool. All right, any question about that? Okay, let's keep going here. So last time we were talking about graph implementations, and we had talked about, man, I better stay close over here. We had talked about an implementation called the edge list implementation that included a vertex structure and an edge structure. And we looked at a smattering of functions and their running times given only those two structures. Last time, though, when we first introduced the idea of a graph as an abstract data type, we mentioned that most graph implementations will have, yes, some structure for the vertices, yes, some structure for the edges, and then additionally an auxiliary structure that helps you keep track of the connectivity of the graph. Okay? So that's what we have here. The structure that we're going to talk about is called an adjacency matrix. The actual implementation of this matrix depends a little bit on how you implement the vertex structure. If the vertex structure is a map, here, all right, vertices and edges. If the vertex structure is a map, then this is probably, or an associative array, then this is probably a two-dimensional associative array. If you implement this as just a regular old array, then this is probably a two-dimensional regular old array, okay? Now, here's how, so given all of that, what are the dimensions on this matrix or array? What are the dimensions on it? You can tell just by looking. It's 4 by 4. Yeah, vertices by vertices, n by n in general. So this is going to be an n by n structure, or, you know, a map that it reflects, or a map that implements an n by n structure. Okay, either way, it doesn't really matter. All right, so here's what we're going to do. If you recall, last time we used the edge structure to keep track of the endpoints for a given edge. So for example, A has UV. I'm going to do this really quickly because it's not really the emphasis of what we're doing here. So, okay. So here's how we use the matrix. That matrix is essentially a Boolean matrix that reflects the presence of an edge in the edge list structure keyed by its endpoints. So for example, edge A has endpoints U and V, and so in this structure we would take cell UV and say it's there, reflect using a Boolean that it exists, okay? And we do that for all the edges in the graph. So for example, UU is not there because this is a simple graph anyway. UW, oh yeah, that's there, and UZ is not. VV is not there, VW is, VZ is not, WW is not there, WZ is, and ZZ is not. Why did I do it that way? What did I do and why did I do it that way? Yeah? Yeah. Right. I don't have to include all that data. That data is redundant because the graph is undirected, okay? And when I say redundant, it manifests itself in the fact that this matrix is symmetric. So I'm going to go ahead and, but all that said, I'm going to go ahead and make those entries anyway, just because it's not that much extra space. And it makes my algorithms slightly simpler. It means the edge cases of my algorithms are more elegantly dealt with. So I'm going to go ahead and replicate the data anyway. Now this is the point at which you realize if this were a directed graph, this is how we would indicate so that it is. Because in that case, for a directed graph, we would not merely mirror the other side of the matrix. That is, edge UV might be in the graph, but edge VU might not. Okay, so this is the point where the fact that this is an undirected graph becomes important. It is undirected though, so I'm just going to make it symmetric. All right, any questions about that? Okay, yeah, Mark? Yes, so the question is, are undirected graphs basically just symmetric directed graphs? Yes, an undirected edge is just an edge going this way and an edge going this way. So all of our streets out there are really one-ways. They're just one-ways in both directions, okay? That makes sense? Or it doesn't at all, right? Sort of silly. All right, any questions about that? Okay, well, I have one more little detail to give you. This isn't exactly the way we would implement this. It is actually convenient to store some reference into the edge structure from this matrix. So rather than storing a Boolean here, we would, for example, there are many different ways of doing this, but we would maybe store a pointer from this location, say from UV, to the location in the map where it lives, okay? And so this one would actually point to here. Or maybe, it's a pointer, it points here, or maybe we just store A here, and we know, given the edge name, we can get to the edge data in constant time. Either way, these are implementation details that you could decide upon if you wanted to. I like the use of a pointer in this context because the absence of an edge, like UU here, could be dealt with using a null. So it's kind of convenient to use a pointer in this case. Here, I'll rewrite it. Okay, any question about that? So the implementation details are just slightly different than the conceptual knowledge here. All right, so all of that said, let's go through our algorithms and talk about, or our functions, and talk about their running times in the context of this setup. And I'll tell you right now, the very first one is the most complex discussion we're going to have. Whoa, what? All right, so we're going to insert a vertex. There it is. There's my new vertex. I know that I'm going to need to put it in this structure, and I know that that can happen in constant time because this is either an array that I can insert in constant time or an associative array. Either way, I can throw it into the vertex structure in constant time. So what's so complex about that? Yeah? Yeah, look, there needs to be room for that guy in the adjacency matrix. Now, it would be nice if all I had to do was this, right? You can tell how long that would take by how long it took me to draw it. But the problem with that is that when we think about doing that in code, it means allocate an array one cell bigger and then copy the data, right? So let me draw a picture for argument. Let's suppose that this is our array and this is the data in our array existing. If there is space when t comes along, then all I have to do is basically claim a row and a column for t. The problem comes about when in fact the array is full and t comes along. What should we do? What should we do? Do you have an idea? No way? Yeah? Double the array. Wait. What does that mean in this context? What does it mean? It means double it in both dimensions, or in this case, the effect is to quadruple it, but that's okay. So we are going to make a new array that is twice as big in each dimension and copy the data. How much data gets copied? N squared, oh my gosh. But look what this gets us. It means that there's room for t. There it is. And it gets us, essentially n future adds that are cheap. So the cost of inserting a vertex then is big O of n squared per n inserts, or big O of n per insert on average. Okay? Any question about that? So the principle is the same, but the actual implementation of it is slightly different. All right, how about removing a vertex? Well, let's remove V. How do we remove V? It's gone. We should do this in red. V is gone. V is gone. Do you like it? Yeah, what's up? What's wrong with it? Oh, there's this shifting it. Wait, shift what? Yeah? Yeah, really good. The phrase you want is incident edges. Yeah? Okay. So, right. So remember, if you remove a vertex, it really means remove that vertex together with its incident edges. We can find those incident edges by noting that they exist either in a row, actually in both, the row and the column indexed by the given vertex, by the vertex that you're removing. Okay? So the algorithm for doing the removal is a matter of essentially zeroing out all of these rows and columns here. Okay? Any question about that? So I think you should be concerned about perhaps having to gather back this space, like having to close the gap in the array. And I encourage you not to have to do that. That in practice, there's really no reason to do that until you have reason to resize things down completely. So that's kind of an implementation detail that we're not going to talk about here. You might refer to it as lazy removal, that you're going to allow for a bunch of removing until at some point your array is really not very full anymore, and then you would resize downward from your given space. It isn't quite this. You want to go actually from the next iteration up to this iteration. Yes? Yep. 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 It's exactly the same process, both growing the array and shrinking the array. Exactly the same. Yeah, Jeremy? Yep. You can't really do that. So I'm gonna throw this back as as kind of an implementation detail where that kind of depends both on what you put inside each of these things together with how you implement this thing. So I'm going to kind of say, oh, that's a question for lab with a specific query on top of it. And it depends a lot on the interface to the graph structure that you're using. All right, so I'm sorry, I'm not going to, yeah, okay. Any other questions about this? All right, so in general, removing a vertex, even without the resizing, I assert that any resizing that you're ever going to do is not going to hurt you all that much. But even without that resizing, in order to remove a vertex, you have to walk down a row and walk down a column to find the incident edges. Okay? And furthermore, zapping them, you assume that you can actually get to those edges in constant time. You have some way of removing them from the edge structure. All right, how long does it take to check to see whether two vertices are adjacent? Constant time. That's the whole point of this table, right? We've got this table, we're going to look it up. That's why we did this. We want to be able to see what edges are in our graph in constant time. Then finally, I want to know if I want to return the incident edges on a vertex, all of them, one at a time, how long does it take to do so? How do I get to the incident edges? How do I find them? What's the algorithm? How do I find the incident edges to a given vertex? Yeah?
Walk along a row or a column.
Yeah.
Everywhere you have a vertex.
Yeah, exactly right. Your only alternative here is to walk down a row looking for an edge. Hey, are you incident on this vertex? Are you incident? You have to walk down the row in order to do it. Okay, so this is big O of n. Any question about all of that? All right, so this is the, just to reiterate, this is the adjacency matrix implementation of a graph. I have a question for you. It's a question about efficiency, but not of running time, rather of storage. Okay? So first I want to ask you, if we're storing a complete graph, is this a good mechanism for storing all of our edges? Is this a good mechanism for storing all of our edges if almost all the edges exist in the graph? Sure, right? We can't hope to do better. We're not wasting any significant space here. Now I'm going to ask you a question about a particular graph and see what you think about this particular implementation. So I want you to think about the graph induced by an image as in MP4. Last time we very quickly, even if I don't even remember for sure that we did, but we referred to the pixels in an image as vertices and an edge existing between pixels if they are adjacent to one another, like this. Okay, and you can imagine that on 500 by 500 of those things. They live on a lattice. Now, I want to know if there are n vertices in such a graph, how many edges are there? There are n vertices. How many edges are there? You can give me a loose bound, kind of. N vertices, how many edges? About. You got it? Did you say it? Oh, no, okay. Oh, good question. There are n vertices total. N is not the dimension of it's not n by n, it's n total. Does that change your answer? N total vertices, n total pixels, n total vertices. How many total edges? Yeah? Upper bound of 4n, and you can do better. Yeah? About 2n, that's right. There are 4n, I want you all to think about this. There are 4n endpoints, right? Because every vertex has degree 4. So there are 4n endpoints, which means you've overcounted the edges by a factor of 2. So take 4n divided by 2. There are about 2n edges. About 2n edges. Is this a good way of storing 2n edges? No, you've got order n things in n squared space. So you might be a little suspicious of using a structure like this for graphs that don't have very many edges. Yeah? Yeah? Uh-huh. Uh-huh. Yeah, so, right, so the question was a good one, and it kind of went through my mind as I was saying the words, but let me respond to it. So I said, is this a good representation if your graph is a complete graph? If your graph is a complete graph of size 500, say, there is only one such graph, right? Heck, we can store a complete graph of size 500 in constant space because there's only one graph like that. There's no connectivity to keep track of. They're all there. But what if your graph is only almost complete and some of the edges are missing? In fact, some fixed fraction of them are missing. So in that case, where you have big O of n squared, then this is your friend, okay? So it's a great question, but I was speaking in asymptotic terms, not in precise terms. Okay, does it answer? Okay, all right. Anything else about this? Any other questions about this? So so you should be a little bit suspicious of this for graphs with not very many edges, aka sparse graphs, and that'll come up in discussion later. All right, so here's another implementation. It will feel more intuitive, I believe. It's called an adjacency list. So first of all, it has the same edge list as before. I'm actually not going to fill those in because it's the same, but you shouldn't either because it's actually a little bit different. And it also has a vertex structure, but this time we're going to explicitly associate with every vertex a list of adjacent vertices, okay? So, for example, from U, I'm going to have V and W. From V, I'm going to have U and W. From W, I've got three things, I believe. U and V and Z. And from Z, I only have W. All right, I've drawn this as a singly linked list, and we'll decide in a few minutes whether that's a good idea, okay? But first, I want to ask you some questions. How many nodes are there in general? If I tell you there are V vertices and M edges, so the size of the vertex set is M, the size of the N, the size of the edge set is M. I want to know if these are implemented as singly linked lists, how many nodes are there total? How many nodes are there total? We're playing chicken. How many nodes are there total in general? 2, 4 is correct. No, wait. 2, there are 8. Yes, in general, for general graphs, if I did this for some arbitrary graph, how many nodes would there be? 2 times the number of edges, okay, because there's a box per endpoint. So again, we're effectively just counting endpoints here, right? When you look at the degree, you're effectively counting the endpoints of your edges. Okay, now, for convenience, we're also going to store those degrees. So you can assume that for every vertex sitting in this data chunk associated with the vertex, you're going to keep track of its degree, just as a matter of convenience. There's really no reason to do so. Okay? Any question about that? All right, so let's start looking at some of our functions here. Let's start looking at our functions. We're going to insert a vertex. What's the running time of that? Of inserting a vertex? Has to be constant time. There's nothing special here. There are no incident edges to plan for, right? Okay, how about, you know what? I actually want to do, oh, I didn't do remove an edge. I'll do remove a vertex because that means remove all the edges. So we're going to remove a vertex. Okay. Here we go. We're doing this in red. Vertex V is gone. Vertex V is gone. Oh, you well know at this point that if we just remove that front thing, we're going to essentially, effectively leak that whole adjacency list, right? So we need to remove it. So, well, all right, I know how to remove things. I'm just going to traverse this thing and free the memory associated with it and fix it all up, right? I'm going to walk down the list, freeing the memory, or doing it from the end forward. It doesn't really matter. Do you like it? What else do you have to do? What else do you have to do? Yeah? Oh, yeah, look. This node right here corresponds to edge VU, right? So we know somewhere in U's list, there's going to be a UV. Oh, crap. How on earth are we going to find it? Well, I'll show you. Here's what these edge lists really look like in the context of this application, or one way of doing this is to, let's see, UV is A. Okay, it's to set up your edge list as it was before, that is, keep track of your endpoints, but also to add into the structure pointers to or references for or some indication of where the endpoints are in the adjacency list structure. Okay? Then furthermore, rather than storing a U here, either store a pointer to that whole edge list entity or store the edge itself. So store A here. Okay? Now, removing that, effectively removing that edge means we're standing here. Okay, we got here in the appropriate amount of time. It means go to the edge list, follow the edge list back to the top node, free it, follow the edge list pointer back to here, and free it. And then go on to the next one. My question is, how long does it take to remove an edge? Using that hop, hop, hop strategy. How long does it take? Hop to the edge list, hop to each of the locations, hop on to the next thing you want to remove. How long does that take? I'm not even hearing anybody whisper it. So I just want to remove one edge. There's a hop to the edge list, a hop to one of the nodes, a hop to the other one of the nodes, and a return back. I just want to remove one of them. It's constant time, that's right. It's hop, 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 right? So removing a single edge is constant time, and then we have to do that once per incident edge. Okay? All right, so you should have a problem with this. You should be like, wait a sec. If this is really a pointer, I wish I were a little bit taller here. Oh, this is really dumb, but whoa. Okay. If this is really a pointer, and I ask you to remove this node, how do you feel about it? What comes to mind? Removing a node by pointer in a linked list. How does that work? How does that work? Can you do it? Yes. How? It's a big fat old hack, right? This is the constant time hack for removing from a linked list. I don't know about you, but I feel pretty skittish about that, especially because this structure is also storing pointers to this one, right? And we're going to remove that puppy and bring it here. I assert that you want some kind of abstract notion of a list here rather than a particular singly linked list. Or you could do it as a doubly linked list if you wanted to, okay? So the technical details of actually doing this, yes, you could make it work, but actually writing the code is different than this discussion that we're having here, okay? Yes? You don't remember how it's constant, what's it in your question? Yes. Okay, so again, I'm going to do this one more time. Removing an edge, and with the understanding that for removing the vertex, we have to do a bunch of edges, okay? Is that all right if I make that simplification? Where'd you go? Who has, oh, there you are. Okay, so is it okay if I just talk about one edge and we all understand that we're going to have to remove a few edges? Okay, so pretend I'm sitting at the node that I want to remove. This edge, WU, I want to remove that edge, okay? I don't know where its friend is, where the other node corresponding to the same edge is. I don't know where that endpoint is. I could, as an auxiliary measure, store UW pointers between these directly. That would be fine too. I've seen that implementation. Or I can keep a reference to this structure for edge UW. Okay, so I can get here in constant time. Yes? Once I'm here, this one will have references to both locations that I'm going to need to get rid of, both endpoints, right? I can do that in constant time because it's just plucking something out of a linked list or a list in general, an abstract list. And then once I have done that, once I've used these to remove them, I can continue on my way to the next edge and remove it in the same fashion. Is it okay? Totally clear? Okay. All right, so, sorry not to make it clear to begin with. All right, so removing a vertex is going to depend on what? Yeah, this is proportional to the degree of the vertex. All right, how long does it take to check to see whether two vertices are adjacent? What's the algorithm for doing so? My only alternative is to go to one or the other and look for the other in that adjacency list. That's the algorithm. What's the running time? Well, which list am I going to go down? Say the shorter one, okay? So this is going to cost you time that is proportional to the minimum of those 2 degrees. Okay? And then if I want to return a set of incident edges, this is really what this structure is built for. This is really what this structure is built for. To return a collection of incident edges is merely one at a time as we need them, say, is really a matter of navigating the adjacency list. Okay? All right, any question about that? Okay. I'm kind of done talking about graph implementations. As I've said before, you know, your implementations are really going to be custom. For example, MP7 is our graph MP. Raise your hand to those of you who have a pound include graph.h at the top of your solution. Not very many, very few, right? You don't actually have to use an explicit graph in order to implement graph algorithms. MP4, also a graph MP. All right, so here's the table that summarizes all the running times. Again, I encourage you not to memorize this table, but rather to understand why each one of these things is true, so that remove vertex should really induce the thought of an algorithm rather than just a result. Also, I want to point out that the people who made this table to begin with were not as clever as we are. They didn't really want to think about smart resizing. Okay? And this came from a textbook, actually. All right, any questions about this? Okay, so we're going to get a start on our next topic here, and that is graph traversal. So graph traversal just means graph exploration. Much like for tree traversal, the objective of graph traversal is to visit every vertex and every edge in the graph, honoring the connectivity of the graph. If I didn't add that piece, then you could say that just iterating over the vertex list and then iterating over the edge list was a graph traversal. And I don't think there's anybody in the world who would accept that as a valid graph traversal. Instead, what is meant by the honoring the connectivity of the graph is that the notion of a next vertex is prescribed by the set of edges incident on that vertex. So the idea of what comes next is constrained by where you can go from a given vertex. Okay, and that's what I mean by honoring the connectivity. The purpose for graph traversal is not usually just to go around and look at all the edges or look at all the vertices, because again, you could do that just by iterating through the graph or the vertex or the edge list structures. Rather, we're usually looking for interesting substructures, like a path from U to V of least cost, or the connected component in which a vertex dwells, etc. We could make this list for about a year. Okay, there are lots and lots and lots of different substructures that you might be interested in looking for. All of our cycles in a graph, cycles of even length in a graph, all kinds of different substructures that you can only get by navigating around on the graph itself. Okay, so to talk about this substantially, I want to contrast graph traversal from tree traversal. Tree traversals have an obvious starting place, right? We always start our traversals on the root. We just do. It's by convention. Furthermore, we always have an idea of where we should go next. That is, we have decided on this left to right navigation. And finally, there is an automatic notion of being done with something that arises from the left to right convention. So done is dependent only on your current location. And it's connected to this idea that trees are ordered, that you have a notion of whether you've been somewhere before. None of that is true in a graph. In a graph, we have an arbitrary start point. Now, in a graph traversal, sometimes that start point is chosen depending on the particular problem that we want to solve, but you can do a traversal starting from anywhere if a traversal is possible. And that becomes a relevant question in the case of not connected graphs. Okay, so we have an arbitrary start point. The order in which we process the incident edges is again arbitrary. You'll notice that in MP4, we very carefully prescribed for you a particular order in which you were supposed to explore the neighbors of a pixel, and we did that because you could have chosen any crazy thing, and we wouldn't have been able to check to see whether your implementation actually worked correctly. So we prescribed an order for you because it doesn't come naturally from the description of a graph traversal. Usually, the order that we choose, the order that comes up in an algorithm is an artifact of how you build the graph in the first place, the order in which you build the graph in the first place, okay? And then finally, there is no notion of being done with no automatic notion of being done with an edge or a vertex in a graph. So if you don't keep track of where you've been, you run the risk of getting lost. I think I've been here somewhere before. Okay? So there is no obvious way, no automatic notion of doneness. Okay? Or of finishing an edge. So you have to keep track. All right, any questions about that? Okay, so our first graph traversal that we're going to talk about in detail is breadth first search. What I want you to tell me before you go, because you can do this in 30 seconds, I have two questions. What is that thing? What is that table? It's an adjacency list, a very shorthand notion of the adjacency list of that particular graph. Fine, what's that? It's 2 lines. What do you think I'm going to use it for, given that we're going to do breadth first search? A queue is correct. This is a queue. Okay? All right, you can go. We'll start here next time.
score is not available in my version.
Your exam 2 score?
Yeah, due to due to the problem error.
Oh,